All right, so I haven't made a video in a while, partially because my P900 is gone, and so I haven't been able to make a lot of the fun videos that I have been making with the super moon, or I didn't get to film the eclipse, and haven't been able to film the sun like I really want to. So I haven't really been making videos because I've been pretty down and out about that. However, this is one video that I've been wanting to make for a long time. This is probably one of the first videos that I wanted to make at all. I actually wanted to do this experiment that I want to propose to you today, because like many of flat Earth people, I sort of came into flat Earth from the perspective, I have a math and science background. I came into flat Earth wanting to disprove that, disprove flat Earth. Like, I wanted to debunk it, like say, okay, there's no way. I watched the first video and I was like, you've got to be kidding me. People are actually thinking like this? This is ridiculous. And so one of the first things I saw was this concept that the horizon always at eye level, or the horizon's always at eye level, right? Or the horizon rises to the eye level. And this is like one of the proofs that they were giving. And I saw some of these videos, that I know you've seen, of high altitude balloon footage where, they're getting like 120,000 plus feet in the air, and the skyline right here, it's like, it's perfectly straight. And it appears that the horizon does rise to eye level, and that just blew my mind. But other than obvious, NASA, supposed photographs, still, even the flat Earth people, still, we don't have any objective, measurement of the curvature of the Earth. We still don't have an objective measurement. We have a lot of anecdotal evidence. We have, the concept that, water never curves, it's always straight. There's lots of experiments involving that. But I wanted to propose an experiment that would 100% prove whether or not the Earth curves at the 8 inches per mile squared down away from you. That is proposed. I mean, that's all that this would propose. That's all that this would show. This experiment that I'm going to tell you right now, I'm going to show you how to do it. It's going to be very simple. I hope somebody does this. I hope once I have the money to fund this, I will fund it. No, hands down. But this is the simplest. So far, I haven't seen anybody do this. And if you've seen somebody do this, and I'm totally in the dark on this, and it's old news, then sorry. But here's the problem. You can take a photo at sea level, or you can stand at sea level. You can hop in a plane, right, and look out, and you can take a photo here. Here's the problem is you physically can't go here to this Earth, right here, this Earth level, this 120,000 feet up in the air, and take a photograph, or see it with your naked eye. So what I wanted to show you is, number one, model what this would actually look like. Okay, right here at this level, if you're 120,000 feet up in the air, and I'll show you the math, and I'm going to show you a model, and I'm going to show you how to create the model yourself. But this is exactly what you would see right here, this picture on the top, this Earth level. This is exactly what you would see no matter if the Earth was flat or if the Earth curved at 8 inches per mile squared, right? At 120,000 feet. You would exactly see a flat, level line all the way around you. And I'll show you why. But you'd have to be much, much higher up before you actually started seeing the circle below you if we were on a globe, right? If there was an end, right? If we're actually on a globe, then you'd have to be a lot farther up than 120,000 feet. And I'll show you why. I'll show you a model, not just some numbers. I'm going to show you a model. I'm going to show you how to model it for yourself. But at this level, using the right instrument, actually using you could use a cell phone to actually discover this. I mean, this is gonna be super simple. It's just, I don't think anybody's done it yet, but you can prove whether or not the horizon rises to eye level or not. Now, what it means eye level, it means perfectly level. That means if you look straight out, the horizon is at your eye level, meaning here at sea level, you don't have to tilt your head downward, right? You don't have to tilt your head downward in order to see the horizon. If you're in an airplane, you don't have to tilt your head downward to see the horizon, right? Now here, this is getting high enough at 120,000 feet or so that you don't have to tilt your head down very much. And I'm actually going to calculate in this model here in a second, show you exactly the degrees that you would have to tilt your head or your camera to be exactly at eye level. Now, eye level in terms of a picture on a camera, just like they have it in these photos, now these photos have been cropped, obviously, but you notice the horizon is exactly in the halfway point of each of these images, right? Or close to, right? Right in the halfway point where there's an equal amount of ground and sky, right? Above, there's as much sky above the horizon as there is ground below the horizon. That means eye level, right? So here, sure, this is probably eye level. Sure, this is probably eye level. If you leveled your camera out, this is what you would get. If you leveled your camera out, this is what you would get. But we don't have any shots, as far as I'm aware, of images taken here showing that the camera was actually at level, right? That it was level with the ground. We don't know what angle the cameras are at this point, which is still, if we could actually go up, shoot a video, take some images where the angle of the camera was being recorded at the same time, you would be able to conclusively prove whether or not the Earth curves at 8 inches per mile squared. So I'm going to show you, number one, I'm going to model it for you. Okay, I'm going to show you how to model it yourself. And then we're going to play a little video over here. Where am I at? Yeah, and then we're going to play a little video here that sort of illustrates what I'm talking about. I just did a little screen recording. So first of all, I wanted to walk you through my process so that you could repeat this. I just Googled radius of the Earth. So the radius of the Earth here, according to Google, is 3,959 miles. And that's the radius, center to outer edge. So obviously it may not be the exact. I mean, there's some other stuff on Wikipedia down here saying there's no natural radius, it kind of ranges, blah, blah, blah. Okay, whatever. It's close to this, all right? So to make the numbers easier, well, first of all, let's convert this to feet, okay? And I'll show you why. We're gonna do a little comparison. So this is the radius of the Earth. If you go over here and you convert in Google, I just search miles to feet, 3,959 miles. Yep. Turns out to be 20,903,520 feet. So what you want to do is you want to make a comparison. You want to compare, what I'm going to do is I'm going to take 120,000 feet, right? Because this is about the level, like all of the weather balloon footage I've seen is about somewhere around 120,000 feet is like, you know, sort of the upper end of a lot of these videos. So I want to model what that looks like. I want to actually create a visual model of what 120,000 feet looks like. So I'm going to compare that to the curve of the Earth, the supposed radius of the Earth, and the curve, and I want to keep it in the same unit, so feet. So 20,900,520 feet. So I just found a ratio calculator.net, and I compared them. I said, okay, 120,000 feet compared to 20 million feet, right, which is the radius of the Earth, is like comparing 1 to what? So I'm just breaking it down. So an equivalent ratio. This is a ratio of 1 to 174. So basically this is saying that the radius of the Earth is 174 times bigger than 120,000 feet is. So that's the ratio. 1 to 174 is the same ratio as 120,000 feet is to 20 million feet, close to 21 million feet, which is the radius of the Earth. So I just wanted to get this a little bit smaller units to work with for our model. Okay, so we're just scaling down the size here. Now, this is, I was a high school math teacher for 4 years. I taught geometry and AP calculus. And I use this website a lot. It's called GeoGebra. You can do insane, you can do insane calculations. You can do insane models and things that are automatically calculated for you. It's phenomenal, okay? But we're gonna use this to create a model, to give us a visual representation and actually calculate angles. That way we don't have to do it by hand. And it'll make it nice and pretty. So the first thing I'm gonna do is I'm gonna take off the grid and I'm going to draw a circle with center and radius. Okay, so it's telling me select center point, then enter radius. So I'm gonna select the center point at 0, 0, and I want a radius of 174, right? Why 174? Because that radius, 174 units, is my scaled down version of the Earth. So this is an exact model of the Earth, just scaled down. Because if I enter 20 million over here, there's no point. This is a much nicer number to work with. So, boom. So since it's all the way out there at 174, I'm gonna have to zoom out, and it doesn't really matter, but okay, there's my globe Earth. Okay, now, oh, whoops, did not mean to do that. Undo. Okay, let's go back to my cursor. All right, so now here's my globe Earth, radius at 174. Now, what I want to do is I want to place a dot up here, right? If I zoom in, I want to place a dot up here that represents the weather balloon, right? At 120,000 feet, which, according to my units, is just 1 unit. Compared to 174, that's just 1 unit. So over here, I need a dot at 175, right? And so point, so I think I can just put a random point here, and then I can tell that point where I want it. It's a point on the y-axis. Where is this? Maybe not. I don't know if I can move this. Oh, maybe I can edit it right here. Let's see. Maybe I'm just forgetting how to do this. It's good. It's a good learning process. Color style advance. Oh no, that's just, I wonder if I can just move it by hand until it's where I want it. Because I need it at exactly 175. You can already see that it's really low. Come on now. There we go. Okay. I know there's a way to actually enter it manually. What can I do? Anyway, I'll have to figure that out later, like actually how to manually enter a point. So there's a point. And as you can see, zooming in, this right here is an exact model to scale. This is a scale model of 120,000 feet above the surface of the Earth, if the Earth is a globe. So now you can see that that's not very far in terms of seeing a ginormous curve. You're not going to see a curve, right? Because you can't see that far out, right? Now, how far can you see? Where is your horizon? The horizon is basically as far as you can see from here all the way out here. It's what we call the tangent line, right? It's the line that you can draw that goes through this point and just crosses the surface of this circle and then keeps going. That's really technically as far as you can see. Now, I don't know if your eye may not be able to tell much of a difference further out you go. Like, so let me just draw that line to show you. So let's see. Line. No, I need a tangent line. Tangents. Select pointer line, then circle corner. Okay, so I'm going to draw a tangent line. So I'm going to draw the tangent line that goes through point B and intersects with this circle. So it's giving me two lines, right? So let me hide this line. So now that we only are seeing this tangent line, right? Now this is the horizon, right? If this is the weather balloon, you're looking down, right? You'd be looking down on the Earth, and you wouldn't be able to see past right here where it intersects. So let me also plot the intersection point. You can see how useful this GeoGebra is at plotting points. Intersect. So you hit intersect, right? It calculates it for you. You don't have to do it. So down here, select intersection or two objects successfully. So I want the intersection point between this line and this circle. Boom, and it gives it to me. So this right here is the horizon, right? If the camera is here above the Earth, this is looking down. You're not going to be able to see past here. Now, all of this from like, here all the way to here, it's probably going to be one blurry line, but that's the horizon, okay? And what we're interested in is what this angle is, right? How far down does the camera or your eye have to go in order to be looking direct line of sight with the horizon, okay? Because on the flat Earth, let me show you. I'm going to draw a line. Actually, I'm going to draw the line. How do I enter this? Oh, right here. Y equals 175. Boom. Okay. From here, this is straight out, right? On the flat Earth, on an infinite plane, if you will, if you take your camera or your eye level, this is your eye level looking straight out, right? The horizon would be here. But on a globe, as you can see, you would have to angle the camera down in order to be looking at the horizon. So the question is, what angle is this? How far down do you actually have to angle the camera to actually see this? And then once you know this angle, this little angle right here, this angle right here, how far down do you have to angle it in order for the horizon to be in the middle of the camera, right? Because down here at sea level, you set your camera, you make it level, and the horizon is in the very middle of the image. But up here at 120,000 feet, you have to angle, if you're on a globe, you have to angle the camera down a certain number of degrees that we're going to calculate in order for the horizon to be in the center of the frame if we're on a globe. So now let me zoom back out again just so you can see the scale of this, okay? I mean, it's not that high. That's 120,000 feet, right? Above the surface. Here's the globe. Okay, it's not that high. So zooming back in, we want to know this angle. Here's the horizon, the tangent line, looking down. We want to calculate this angle. So I go over here, angle. So it says select 3 points or 2 lines. So I want to know the angle between this line and this line. Boom, and it gives it to me as, oh, it calculated it the other way. No, I didn't want to put point D. Oh, you know what? I should have done it the other way. All right, let me calculate this way. Let me crud. All right, angle. Maybe if I go between here and here, it'll give it to me. This line and this line. No, and this line. Where's this point D coming from? All right, this line and this line. There it is. Whew, finally. All right, let's see what this angle is. Can I move this? Because I can't see it. 6.13 degrees. 6 degrees. I'll put it right here. It's 6 degrees. So you have to angle the camera 6 degrees, 6.13 degrees down in order to see the horizon in the very middle of the camera. Okay, so now you can repeat this. You can actually play around with this. This is a phenomenal tool. So 6 degrees, that's the magic number. Now the question is, how do we actually do that practically? Okay, and now this is what I'm going to show you this video on exactly how to do that. Now, can you actually determine 6 degrees, right? Half of 120,000 feet is 60,000 feet. You know, some airplanes, I guess most of the ones I've flown on are around 30 to 40,000 feet. So it would be, the angle would probably be, you know, around 3 degrees, which is why you're not going to be able to discern whether the horizon has dropped 3 degrees, you know, like just visually. But 6 degrees, I think with a camera, right? Like, you know, can you tilt your head 6 degrees downward? Do you know if you're looking out at a horizon way out there, do you know, can you visually tell, you know, 6 degrees? And it doesn't matter anyway. We want to be able to objectively measure it. So check this out. This is an app I downloaded. I'm on an Android, and I think it's called Open Camera. So there's no ads. It's free. Pretty cool. But look at the features. The features of this are that, well, here, let me just play it. Check it out. Number one, it uses the sensors on the camera itself and gives you visual feedback. So it tells you when your camera is level, right? And you can see the degrees, right? -5, 0 degrees. It will also tell you how far your camera's angled. So look here, on this image, can you see how far in terms of pixel distance 0 to 5 degrees is, right? And we're talking about 6 degrees. Okay, so let me play this and let me show you how it changes. All right, so here's me trying to essentially level out. All right, so right here. So let's pretend this camera, I've got this camera in a weather balloon and it's 120,000 feet in the air. If it's 120,000 feet in the air, this is your horizon. This little row of hedges here is your horizon, okay? If you could have this app or some app similar or a gyro or something similar here that's measuring the angle of the camera, as it's recording and as it's taking pictures and video or whatever, every time you could just look to see, is the horizon at 0 degrees? Because if, and I've never seen anybody do this yet, so if there is, please link a video, send me a comment, because that is absolute 100% proof of curvature or no curvature, right? Objectively measured, right? That's objectively measured curvature or no curvature. Because if, I mean, look at this, 6 degrees. Remember we measured 6 degrees right here. The camera would have to tilt 6 degrees down for the horizon to be in the very middle of the image of the frame. Come over here, look how far down 5 degrees is, right? I mean, you could actually screenshot this and count the number of pixels from 0 to negative 5 degrees down. You could actually calculate the number of pixels per degrees. But look at this. This is like a third or a fourth of the entire vertical length of the image right here, right? But all the pics we have, it's like floating around, and you can't tell. You never can tell where the angle is. The angle's never there for you at the same time. So yeah, it appears to be that it arises to eye level, but we've never objectively measured it. If you did this, right, it would conclusively prove it. So see there, I'm steadying it at that. So there's the horizon. Now look at what I'm doing. I'm tilting it down 5 degrees. Obviously, I kind of moved a little bit, but do you see where the center of the frame is now? The center of the frame is way down here at 5 degrees, which is basically saying that this is how much you would have to tilt your camera down all the way to 6. You'd have to tilt it all the way down that much as I just did in this video, in order for the horizon to be in the very middle at eye level, well, not eye level, but in the very middle of the frame if we're at 120,000 feet, okay? So this right here, if you did this test, right, we need something like this. We need to send up a camera at around 120,000 feet that as it's recording and taking pictures, it's simultaneously recording the degrees. Like, is it centered? As far as I know, this is possible. I wouldn't see why this wouldn't be possible. So forward this video on to somebody that can get some of this stuff done. I currently don't have means. I'm actually still in school right now. I've got a few months left before I'm out. Working on my doctorate degree actually. So that'll be a few months before I'm out, so I'm not making that doctor money yet. So I can't fund this yet. But as soon as I can, I would totally fund this. I don't know how to do it, but if we could get together the plans to do this, man, like create a GoFundMe or something, get together with the guys that have already, put weather balloons up. I know a lot of them aren't looking for this, but this right here is the only way that I've been able to come up with to objectively measure whether or not there is a curve to the earth. If at 120,000 feet, if you're simultaneously recording the angle of the camera, if when the camera is at 0 degrees, perfectly level, if the horizon is right there even, that means conclusively the horizon rises to your eye level at 120,000 feet, and we are not on a globe that curves at 8 inches per mile squared. If, however, when the camera is down at 6 degrees, if that's where the horizon is, then that conclusively will prove that we are on a globe, and that it shrinks away from you at 8 inches per mile squared. So right now you'd still see, remember, one last thing before I go, remember, you would still see this, right? I mean, you'd still see a flat line. You wouldn't see a curve. You'd have to be so far up. You have to be so far up to see, before you would actually see any curve to the left or right here, which means you can just see right here. You could even double your distance and you're not really going to see a curve, right? If you look at this ratio, this is a 2-scale model, and you can play around with this and do all sorts of fun stuff. But if we zoom out, I mean, you can see how far up you'd have to be. I mean, you'd have to be like way up here and then looking down before you'd start seeing, right? Even if you were here, right? Where's the tangent line? The tangent line's still like right here, you know? So anyway, that's my proposition. That would conclusively prove this right here. For a fact, it would be objective measurement of the curve or no curve. And I think that would be, incredible, because if you had that, no one could argue with it. I mean, literally, like right now, all we have to go on is, it looks like it's at eye level. Of course, it's going to look like it's at eye level, but have you measured it yet? Have we objectively measured it? Once we have that, oh my gosh, it's going to be like no one could argue. No one. All right, so let me know what you thought. Love to hear some suggestions. Once again, this channel, I created this channel specifically to provide value to the flat earth community. This is not a debate channel. Honestly, if you start putting stuff in the comments, like, I'm, like a lot of the trolls, I mean, I expected, it's been on my videos. I've seen all of my videos. I don't want either side. I don't want flat earth people or globe people putting any kind of hate out there. We don't need any hate. We just need some rational, pleasant conversation. So I invite all of that. You can definitely personal message me on YouTube. So yeah, just looking to increase the value of the entire flat earth community. So let me know if that was valuable, guys. And I really want to see this experiment.